Yeah. I think we saw that. Yeah. I keep forgetting about that, and every now and again I'll click on the captions and it's turn the sound down and just watch it that way. It's like a stream of consciousness or something.
Yeah.
Alright guys, so I want to focus first on going over anything over what we did last time that still does not make sense. So hopefully you got this to a point where it's ready to be turned in. We are going to talk really quickly about anything that gave you trouble, and then I want you to turn your stuff in. Any questions from that review?
We didn't get one of those. That's a handout. I don't know what that is.
Yeah, it's the group work we did. Well, it is from the book, but it's just not the homework. Right there. Yeah.
Does anyone have a statement? I'm going to be the first to ask. No,
I do.
Jeff does.
As I said that, I was like, do I really?
Number 24.
24.
Find the inverse function.
Yeah.
Beat me to it. I did.
So generally, what's the process to find the inverse function? Good, I love it. Wait a second. So bring y back into it. Switch x and y. And then solve for y. All right, and this is a problem you don't really get a lot of practice with, but it's the same idea as always. You get all of the thing that has your variable in it on one side, and then you can divide at the end. That's what you do. So I want everything with the y in it to be on one side. The most important first step is to take care of the fact that there's a fractional part of it. So of course the first step is going to be multiply that up. So I can multiply that up. Is that cool? Now you want everything with the variable you're trying to solve for on one side. So what do you want to move away from here?
Move the x to one side.
Probably the thing I just pointed to. Yeah, the non-y thing you want to get out of there, and any y stuff you want to get over here. So these are just going to switch really. So far so good? So it's the same thing you learned from day one of solving equations in algebra class. Get your x's on one side, your variables on the other side, your letters on the other side. Get your y stuff on one side, that's what we're solving for. Your other stuff on the other side. And the weirdest part about doing this is the fact that there's two y's, and I'm saying no, there isn't two y's. There's one y that I can pull back out. And then of course the last step.
Divide by 2x.
Yeah, the last step of solving equations is almost always divide. So we end up with f inverse is 1 minus x over 2x minus 1. Now if you're really bored and you're just like, let me do some extra math, how do you check that to make sure that's right?
Oh, you plug in points?
It's not good enough. You could just happen to pick points that work. Right? In order for this truly to be the inverse, it's got to work for every single point in existence. I don't want to take that much time out. Plug that into this, and you should end up with just x. They should cancel each other down to just x. I don't want to do that. That's how you would do it to check it. I feel pretty good that's it, so I'm not going to check. What the hell? Well, I mean, the idea is pretty simple. It's just that sometimes we don't do this kind of problem enough to kind of have it as just, on the tip of our tongue. But that's how you do it. Get the y's on one side, factor it out, divide by the crap you don't want. You're there. So that was number 24. Any other ones?
18.
I think I heard, 18.
Yeah.
Oh, yeah. This one was fun for everybody. So a really good first step here is to graph this, because this is not that involved of a graph here. So from negative 2, 2 to negative 1, 0, it's a line. And then it becomes the top part of the circle, centered at the origin with radius 1. Well, that's kind of nice, like that. So if you didn't graph that, hopefully you could. And if you did, hopefully it looks sort of like that. Maybe just a little better. Is that cool so far? So it's a line segment from that point to that point, and then it's the top half of a circle, radius 1. So it's going to be 1, 1, 1, center 0, kick-ass. So now the whole point is, okay, Jeff, you graphed it. They don't even ask for the damn graph, do they? They want it written as a function. So what kind of function will this be?
Piecewise.
Piecewise. So you know the format's going to be this kind of thing, x, some definition of where it's true. So you've got to figure out the equations for both of these. This is just the equation of a line, negative 2, 2 to negative 1, 0. Right, do your whole mx plus b and blah, 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 and hopefully that's not a big deal. Right, what's the slope?
Negative 2.
Yeah, negative 2. You don't have a y-intercept, but we don't care. Right, we can attack this. The quick way to do it is use y equals mx plus b directly. Like for this one, y is 0 when x is negative 1. So b is negative 2. So you know, for the line segment, it's negative 2, x minus 2, on what interval?
From negative infinity to
Careful.
negative 1.
The line segment specifically goes from that point to that point.
Okay, second.
Yeah, for x equal negative 2 to negative 1. They told you when they gave the points, they actually told you the interval for the first part. So the whole thing about piecewise functions is that they're defined on very specific intervals on the x-axis. It's a line from this to this, and then it's a circle from this, and then it's a parabola from this to this, or whatever. So I have to have that part here. It's a line from negative 2 to negative 1, and then the circle takes over. Okay? How do I find the equation of this circle? What is the equation of the whole circle?
X squared plus y squared equals 1.
So the equation of a circle in general that's centered at the origin is this. Hopefully that's familiar. And again, I'm going a little quick over this stuff because this should be reviewed, right? For some of us it might be a little while, so it's got to come up out of the deeper parts of our brain. The radius here, of course, they told us is 1, and I can't put it in this format until I solve this for y, because I have to have f of x equals something, right? And it's the top half, thank God. Why is that important to know here?
Because when you get the square root, you get the negative.
Yeah, when you take a square root, you know the y is squared. At some point you got to take a square root. That means plus or minus in general, but we know we want the top half. We're going to take the positive. So when you solve this for y, you subtract the x squared. You take the square root. You want the positive one. So there it is. So from what to what? Yeah, negative 1 to 1. This is defined to be square root of 1 minus x squared. Now, in general, this shouldn't overlap like this. And they would have had to be really specific about, I mean, if the line would have went here, they would have to be really specific about which one gets an open circle. Otherwise, it wouldn't be a function. But in this case, they weren't very specific, and they do line right up. So it really doesn't matter at this point. It's still a function because the points here and here are at the same place. Does that semi make sense? If they don't line up, one of them's got to be open. Well, they do line up, so who cares? It's the short of it. Right? Cool, and that's it. So you got your line, and you got your top part of a circle. So what would this be the graph? What would this be the function representing?
That would be the bottom half of.
Sorry, bud.
It's all good.
Well, these guys get a chance.
Bottom half of the radius of 4.
Good. The bottom half of a circle, radius of 4. I love it. Sweet. Just because the negative part out there, r squared would be 16, so r would be 4. Sweet. All right, cool. Anything else from there? So that was 18.
Yeah.
Yeah. Oh, yeah. All right. This one I expect questions on. So 20 is 19 in reverse. Right, 19, they give you the functions and then they tell you how to put them together. 20, it's already put together and they're asking you to tear it back apart. What functions went into creating this thing? So let me give you, let's start off with an easier example. Because the problem I gave you is actually kind of rough as a first problem in this kind of thing. But if I gave this here, you can do it, Jeff. What do you got? Well, it might be kind of evil. Still, let's not make it evil at all, Jeff. That'll work out. Okay. So if I had this function here, there's a lot of different answers to this kind of problem, by the way. So one thing that makes this difficult is they ask for 3 functions that go in. So let's just start looking at 2 functions that go in. So what I really want to know is what function was put inside of what other function to end up with this. And there's quite a few answers. The simplest answer would be, well, I put an x inside of this. Yay. And I don't want to see that crap. I want something a little more interesting than that, right? So somebody give me another possibility. I mean, I know the outside function. Now let me see, if I say the outside function, does that make sense? Like the outside function has got to be a square root of something. That's the outside function. The inside function is something, some piece in here. So if I say this came from g of h of x, I know the g of x has got to be square root of something. And the h of x would be what I put in there to make this. So as an example, let me show you what I'm thinking. If I say that g of x is 4 minus x squared, what would I put here to make it this?
4x.
No, 4 squared is 16. Try again. What would I put there to make it this? 2x. All right, so if h of x is 2x, if you plug that in here, 2x squared is 4x squared. And there you go. So h plugged into g gives me this f. So they're asking you to take the function they gave you and do 3. One function inside of another one, and then plug that one into the third one. So it's like the turducken. You guys stuff the duck inside. I don't know which order. Just who cares? Get them all in there and fry that sucker, and make sure it's not going to kill anybody. All right. So the function they actually give us. I like that. Calculus taught through this prism of turducken. They give us this funky ass function. Let me see if I remember it now. But let's see if you guys can pick out what was really important about what I just said. It's kind of important to realize what's the outside function and what are the possible inside functions. So what's definitely going to be like the outside function? What is everything being plugged into? What's the... I love it. So if we're saying that this came from g of h of I, they want this broken down into 3 parts. Holy shit. Right? I definitely know that G is going to be 1 over x. That is one possibility. There's always at least 18 billion ways to do this. Right? And I know that I of x, let me see if you guys can see what I'm talking about. I of x has pretty much got to be the square root of x in a way. And again, there's a lot of different ways to do this, and some of them are kind of stupid, trivial, playing around with shit. But the main thing is, square root of x seems to be the innermost thing. Now here's where things get really complicated. I don't know if you guys are actually with me or not, but this is, let's see. So we got the idea of the outside function. It's definitely 1 over x, and somebody's plugged stuff into it. And what's the innermost thing that's been plugged in somewhere is square root of x. So that's going to be the innermost. And sure, that's why I called it I. Why not? It's not really true at all. And so what's the middle dude? He's got to be that one thing that actually makes it look like all of that. So you're thinking the other way around from what I'm thinking, which is great. If you switch these, that'll actually work. So let me write that down. Idea 2. If I call g of x 1 over x, and if I call h of x square root of x, and I call I of x, so what am I plugging into here?
X plus square root of x.
Yeah. I love it. Right? And I just happened to be thinking about a different way because somebody came by for some help, and they had done it almost all the way this way. How in the world would I kind of salvage this way here? Think about this. Why can't I just put this down here?
Because you have to put x both ways.
Because if you plug a square root of x in, you get square root of x plus square root of x, not this. So what's got to be true about this dude if I actually want this to end up still being x?
X squared.
There you go. So that salvages it. I'll let you guys... There's a lot to let sink in from that. The fact that you have to... If you put x's in multiple places, you better make sure that they actually do what they're supposed to do at the end. Right? That's a good skill to have, yeah.
Idea 2 was correct.
Idea 2 is... I love it. It's a lot more straightforward. So that's the one I'd rather go with. Idea 1 is just the first thing that came to mind when I was helping somebody else out. They were already kind of like halfway through. And that's how to kind of salvage it at the end. But there's 2 different ways to do this. And, you know, like I said, there's a ton of other ways to do this. So if anybody feels adventurous, maybe try to come up with some 3rd idea, 4th idea. Or not. It's all right. Okay. Of course, those at home, you guys can't see as well. Anything else? Any other questions? Sweet. All right.
26A.
Let's see. So how do I solve exponential equations? What do I have to use? Yeah, so if I have e to the x equals 5, just take natural log of both sides and you're done.
Okay.
The one that was more interesting was c, and you just do what we just did twice. Because you have 2 e's to a. Right, so that makes sense, e's to a power. So then I need to use 2 natural logs to kill those. Part D is kind of the easiest and the weirdest at the same time. I don't know why they put this on. It's really silly. What's the answer? What's x? Yeah, x is tangent 1. You just take the tangent of both sides. That kills that, so you get x is tangent 1. I'm not going to write what tangent 1 is because it's not pretty. So just keep it as tangent 1. So it's the hardest easy problem on there. Let's try to go further. If you think it should be something, no. Just stop right there. Okay. So anything else? Is that... You guys remember how to test for odd and even symmetry? Just plug a negative x in, yeah. So if you have a function, so the test for odd, even symmetry. All right, assuming if you plug a negative x in, it's the same as it used to be. That's like what a parabola does. You plug in a 2, it's 4. You plug in a negative 2, it's 4. It doesn't care. It's just, it's always the same output. Even if you just change the sign of the input, that's even. Why does it make sense? X squared, even power, kick ass. That's why we call it even. Symmetry. So it's got even symmetry. If f of negative x is the opposite of the original, and that would be like a cube. 2 cubed is 8, negative 2 cubed is negative 8. It's the opposite of what it was originally. That's odd symmetry. And of course, if it's neither of those, it's neither. Symmetry is very hard to do. You have to kind of set it up perfectly. Most things, if you just draw something arbitrarily, it's not going to have any symmetry. Right? So don't freak out if it's not either one. A lot of things shouldn't be either one. Okay. Cool. Any other questions? Yeah.
What about G on number 1?
G? Oh yeah, so that's sort of like what we're talking about right now. They didn't give us an f. They didn't give us a function, so we can't plug a negative x in. But we can see if it follows either one of these ideas. And sure enough, on 1, that function, sort of like this. So it looks like odd symmetry through the origin.
Okay.
Whatever this is, the negative of it gets the negative output. It's the opposite of what it would have been on the other side. So that's odd symmetry. Am I absolutely certain that it's exactly odd symmetry? No. I just got a picture. But that's all they want is, does it look like it's even or odd? It looks like it's odd. Cool. Anything else from that?
19C.
Oh, yeah. Yeah. So 19C says, and I really hate this. I don't know why they still have that. It just means f of f. Right? If you had like multiple, that doesn't do you. It still looks crappy. If you have a bunch of parentheses, it doesn't help either way. So I'm like, just get rid of the fofo freaking symbol. I don't understand. Anyway, so this says plug f into itself, and of course f was ln, right? So if you plug ln into itself, you get ln of ln. So that's what f of f is. So far, so good. And now the real hard part sometimes on these problems is what the hell is the domain in this? And the first step on the domain, you don't care on the first step what the hell's in there. You just know that since it's the natural log of something, what must be true about that something? It's got to be bigger than 0. Then you care about what the hell this is. You're like, okay, how the hell do I solve that? Well, when does natural log of x equal 0? When is that true?
Never.
Yeah, it does. E to the 0 is 1. So when x is 1, it's 0. So when is it bigger than 0? When x is bigger than 1. Done. So very often the first step will be, and this happens a lot in calculus, and in fact a lot in math, the first step, there's part of it you don't care about, and if you do care about it, it's going to throw you off. I don't care what the hell's in there. My first step is that's out there. So whatever the hell's inside, it's got to be greater than 0. Then I worry about what the hell that is. I don't start thinking, well, what's the natural log of an? I don't care. That's not part of the question. It's just a domain question, and then I just look at this. What's got to be true about its inside? Okay. Yeah. Oh, where did 8 go? Here's 8. Okay. Oh, 8's kind of funny. So 8 was the find the domain and range, and the function's 3 plus cosine 2t. So then your brain starts to say, okay, what's it when you put a 2 inside? What changes and all this kind of crap, and all that stuff doesn't matter. Right? It doesn't matter. Does putting something inside affect the output of the function? No, it doesn't. Right? What's cosine of anything? Got to be between. -1 and 1. And cosine of twice something, does that change the inputs? Does that change what I'm allowed to put into it?
No, it changes how.
It's going to be, what's the domain still going to be?
-1.
No, come on. What's the domain? What am I allowed to plug in? All real numbers. All right, so negative infinity up to infinity for the domain. I could plug in anything I want to, right? But what's the range going to be? The range of that is negative 1 to 1. Now just add 3 to both of those extremes.
2 to 4.
2 to 4. So it is kind of evil. I mean, at the early start of your work, the hardest thing as a student is what exactly is important about this problem? What do I really have to worry about? I could have put any number I wanted to there, and it would have still been the same answers. Right? Because that number is just going to change the compression. It's just going to change, my infinite spring gets compressed or elongated. Who cares? It's still the same output. It's still the same inputs. Okay.
Why wouldn't the range be affected by that too?
Because this just affects how quickly it gets through its cycle, right?
Oh,
It doesn't change how far up and down it goes. It just changes how quickly it gets through it.
I was confusing the two.
Cool. How we doing? All right. Yeah.
19A.
Oh yeah. Yeah. So F. Now this is what's normally the way it looks when you first teach this. So I always tell my students it's like you're in a fog. So like just get rid of that stupid notation. F of g of x. So you're plugging what into what? You're plugging g, which is x squared minus 9. You're plugging that into f, which is ln. So then you end up with ln. So I'm sure the question is on what's the domain of this thing, right? And again, same thing we just did. What's got to be true about the inside? X squared minus 9 has to be greater than 0. And you cannot solve this directly. You can't add 9, take a square root, because then you got to be real careful about how does that affect how does that affect the inequality. But this is a parabola. This is easy. When is a parabola, and what's going to be true about this parabola? Is it open up or down? And what's its roots? 3 and negative 3. So it's opening up. Where's it going to be positive? Where's the positive? Negative 3 and down. Right? So how do you write that in interval notation? Negative infinity up to negative 3. Don't include that because you can't include 0. And then on the other side is just going to be 3 to infinity. Cool. It's when you try to start plugging in stuff smaller than 3, you're going to end up with a negative number in here, right? So it's got to be all the stuff that's bigger than 3. Either 3 or negative 3, because the square makes it not matter if it's 3 or negative 3. Does that make sense? Okay, good. Okay. So let's do this. I have one last, I guess I'll call it a diagnostic like they do. No, I don't want you to power off. Oh, wait, okay. Turn on. Okay. And this is the one you might have been dreading, or you might have been hoping would happen.
It's been a while.
So this is why I do it this way, and we're going to do this together. But I want you to realize, if your trig is rusty, get it up to speed. I will expect you to know your basic identities really well. I'll expect you to know this, like number 4 should be quick. Let's do that first. 4, ABC. Try it out. I don't want to see any typing in any calculators. Or any talking to any thing on your phone that will understand what you're saying, or anything. Huh? I'll tell you this, there are trig review workshops they're trying to put together. So they can find somebody to run them. I'll tell you when they're happening. If you need a trig review. I'll also... I'll tell you what, if somebody emails me and reminds me, I can put up on the website the handout that I give my pre-calc students when we go through the trig section. The Math Study Center has some handouts that are sort of similar. And if you do, nowadays, studying is so damn easy. Go to Google, type in trig circle, handout. It's silly. I mean, it's kind of silly. You desperately need to get back up to speed on these things. So how are we going with number 4? Yeah, 4a. What is pi over 3?
60 degrees.
It's also known as 60 degrees. So tangent is 60. I like that. 1, lower, 2, higher. The way I remember this, I actually never memorized tangent stuff. What I do is tangent sine over cosine. And I don't know how you were taught. And I don't know if my last pre-calc class, some of you guys are here, so maybe you like this and maybe this wasn't a deal breaker. But I always remember that cosine likes x, sine likes y. That makes so much easier. SOHCAHTOA is nice, but it doesn't extend well. So it gets you through just what it does, but it doesn't extend its ideas. If from the beginning you were taught that sine likes y, cosine likes x, as long as the angle's in the base, you're golden. So tangent sine over cosine, it's 60 degrees. Sine likes y, that's closer to y, so sine is bigger. So it's root 3 over 2 over 1/2, which is root 3 over 1. It's root 3. So I never memorized the tangents just because I can't get them to stick, so I don't care. I know tangent sine over cosine. Are you guys kind of with me? And I don't know if you guys have ever shown, I think more and more teachers are showing this. Sine here is 0, right? And then at pi over 6, sine is 1/2. So it's like square root of 1 over 2. At pi over 4, sine is square root of 2 over 2. At pi over 3, sine is, we're at 3 over 2. And at pi over 2, sine is root 4 over 2, which is 1. Root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2. There's a nice pattern, right? And of course, cosine just does the opposite. And once you know the first quadrant, you know them all. Especially if you know sine likes y, cosine likes x. Where y is negative, sine is. Where x is negative, cosine is. I mean, that extends all the way. SOHCAHTOA sounds like a place you go for summer camp. Right? And it works, but it's not extendable. That's why I don't like those kind of things. And people kind of rebel against me when I tell them I don't like that. They're like, well, it works for me. It works this far. And how much more do you have after that? To that wall. So that's a lot to leave out. Okay. So about 4b. Now, of course, in 4b, it's important to realize what quadrant you're in, right? Yeah, which quadrant would that be? Yeah, good. It's 1/6 past pi. Pi is 180, so you're in the third quadrant. Sine then should be negative. And the reference angle is like 30. Good. So sine of 30, closer to x, doesn't like it. So it's negative 1/2. Good. Right? the closer you are to the x-axis, the smaller sine is, because sine doesn't like x. Sine gets bigger when there's more y to it. That's the way I remember it. I don't memorize it. I just kind of think, where am I? And bam, there I am. Then part C, quadrant. Which quadrant are we in? Fourth quadrant. All right. How far away are we from the x-axis?
60 degrees.
Yeah, pi over 3, so 60 degrees away. Yeah. And secant is related to cosine. So the cosine in this quadrant is going to be positive, negative? Positive. All right, so it's going to be positive. Cosine of 60 is... Yeah, cosine likes x. It's far away from x, so it's going to be small. So it's 1/2. Cosine would be 1/2. So secant's going to be 2. I like it. So that's the kind of stuff that you have to be able to do at least that quickly. Right? Because that's going to be little parts of problems all over the place, and if it takes you a long time to do them, you're not going to have that much time like on a test or something. You have to know those pretty well. So let's back up here. Are conversions okay? Does anyone remember how to convert? I mean, essentially, it's one way to convert is just replace pi with 180 when you're going from radians to degrees, because pi is the same as 180 degrees. They both cover the same amount on the unit circle. And in general, if you wanted to get it, like I had 4.7 feet of something, how many inches would that be? One way to do that is to set this up. So this looks familiar to anybody. If you ever had chemistry, you definitely do a ton of this stuff. But it's a unit analysis to make the units go away. So 1 foot, 12 inches, then you multiply. So if I have 300 degrees, I want to go from degrees to radians. 180 degrees is pi radians. And then you just divide and then put a pi at the end. Is that cool? Not a big deal. Some of you guys will look at me like, yeah, that's a big deal, dude. What the hell? That should not be too much there. That should be a nice problem. And then for like number 2, you got to be really careful. If I said convert and I just have a 2 sitting there, it's radians. It doesn't say degrees, so it's understood to be radians if it doesn't say degrees. So how do I convert from radians to degrees? I want radians to degrees, so pi radians, 180 degrees. So it'd be 360 over pi. You can divide by pi and approximate it if you feel like it. Is that cool so far? Is that? Okay, all right. Oh, what about number 3? Who remembers anything to do with that? It sounds harder than it is. Yeah. So when I have kind of a sector, this length, here's the radius, here's theta, S is r theta. So if the length of an arc of a circle with radius 12 centimeters, okay, cool. The radius is 12. The arc subtends a central angle of 30 degrees. Now here's the key. Which one, when you're in doubt, should you use? Degrees or radians? Radians, because it's the real deal. That's the real units. Degrees is something we completely made up. We completely made it up. 360 is a good number because it's divisible by a lot of things. So we can break it up in all these parts. But it could have been 400. It could have been 1800. It could have been 3. We just totally made it up. So I cannot plug a 30 in there. Essentially, in general, if it's not inside of a trig function, it's got to be radians. Unless you have some funky-ass function built off of degrees. So this is not being taken a trig function of. That's a very interesting statement. My grammar's neat. So I have to have this in radians. That's going to be real numbers. So 30 degrees, of course, is 5 or 6. And then I can figure out what S is. S is 2 pi. All right, good. And they gave me radius in centimeters, so it'll be 2 pi centimeters. Radians is kind of weird. It kind of gets out of the way when there's some other unit come in. Radians just kind of steps out of the way, and there it is. If you take any physics at all, you get a lot of r times theta kind of things. The theta times the r gives you like a real value to that. You see that a lot in angular acceleration and stuff like that. You see that happen a lot. So if you're going to take any physics, when you get there, say, oh yeah. Number 5 talks about that over there. So it says express A and B in terms of theta. So what would A? So let's do it this way. Here's theta. Yeah, what would you use to talk about A? You'd use sine. Sine theta would be A over 24. So A is 24 sine theta. And remember, sine is, the outputs are between what and what? Negative 1 and 1. And very often the negative part really kind of tells me the direction it's pointing, in a way. So I always like to think of, and this is actually kind of true, sine is the percentage of this guy that's in the y direction. Cosine is the percentage of this guy that's in the x direction. So if I want to break them up, right? You guys kind of with me? So when you change lanes in your car, you have a certain percentage of velocity that's going that way. Otherwise, you wouldn't go in that direction, right? Of course, hopefully it's not a large percentage. You're not one of those people that go, change lanes, go! Right? So of course here B is pretty simple now. I probably shouldn't have to set this up. Yeah, B is 24 times the percentage in the x direction. There you go, cosine theta. Okay. Maybe. Oh, cool. Try number 6. So some of you guys, when you read through that, you might be saying, I know what do I do? So obviously, hopefully, nobody's putting just a 1/3 in place of x or something. Sine x is 1/3. What is it that you really need to be able to remember to start this thing off? Trig identity for the sine of a sum of angles, right? Who remembers that? All right. Yeah. So the way I taught my pre-calc students was sine is the nice function. See how it gives everybody a turn? I'll go and then you'll go, and I keep it the same sign. If it was cosine of x plus y, cosine's the asshole. He says, me first, screw you guys. You have a plus, I don't care. I mean, that's the kind of stuff that's going to stick in your head, right? I mean, that's the way I always did it when I was a student. So if that doesn't work, don't do it that way. But to me, that it makes it easier to remember these identities. Now I just start plugging and chugging. If sine of x is 1/3, secant y is not very useful. Of course, what do I change that into? Cosine y. So I know sine x is 1/3. I know cosine y is
4/5.
4/5, 11. The reciprocal of that. So I got sine x and cosine y. How do I get cosine x and sine y? You could draw a triangle. You could use the most basic trig identity, sine squared plus Cosine squared is 1. Those actually end up being the exact same thing, because when you draw the triangle, you use the Pythagorean theorem, and that's really what sine squared plus cosine squared equals 1 is. So they're both the exact same work. So if you draw the little triangle for this dude, what does this represent? What sides would this be?
Opposite over hypotenuse.
Yeah, one would be, what would be a hypotenuse? 3. And 1, the bottom or the side? Side, 11. Because that's, of course, the ratio, the sides that are in the ratio for sine. So cosine of x, I have to figure out what that side is. What's that side? I love it. So 9 minus 1 is 8. Radical 8 reduces down to 2 rad 2. So cosine of x is 2 rad 2 over 3. If you are completely lost in this discussion, you have desperately got to come see me or see a tutor. Right? Soon. You need to have this trig stuff down. So the same thing with here. Let me do this one the other way. So you say sine squared y plus cosine squared y equals 1. So sine squared y plus 16/25 equals 1. You can pretty much eyeball this and see it, hopefully. This would have to be 9, right? The missing.
9, yeah.
So it'd be 9/25. So sine squared has to be 9/25. So sine y. And this is why they had to tell me what quadrant I'm in. I know they take the positive one because they told me I'm in the first quadrant. You guys with me? That's key. So they had to tell me that, so at this point I know which sign to take when I take a square root. So now I can just plug and chug everything. Everything look all right? Of course, here that wasn't even that much work because you should know the 3, 4, 5 triangle. But I at least want to show you how the sine squared cosine squared thing works. Okay. And now you just plug and chug. Sine x 1/3, cosine y 4/5, plus cosine x 2 rad 2 over 3, sine y 3/5. So I get, can't read your own writing, 4/15 plus 2 rad 2 over 5. So 4 plus 6 rad 2 over 15. Or don't combine them. I don't care. Either way. Yes?
How could you get sine y using the triangle?
Oh, same way you would say cosine would be this 3, 4, 5 triangle, right? And then 3/5 for the side. Yeah. That's why I pretty much default to the triangle, because once you start doing this, you get a little lost in this, and you're not stepping out and saying, oh, it's easier than all that crap. I know what that number is. How's that so far? All right. And then I'm not too worried about it. I mean, the rest of it we'll pick up as we go, as we need to, right? I'm not going to make you prove identities anymore, but I will expect you to remember a lot of the identities. I forgot I should be more firm on which ones I want you to remember, so I'll bring that next time. It's my pre-calc students, it's basically the same ones. I don't make you remember like power reducing formulas. Does that even sound familiar? Yeah, okay. Because the whole point is lost. If you're memorizing it, you're not realizing that I can just get that from the other identities. There's very few identities you have to memorize. You can build off of those to get the rest. Okay, so everybody got what they need here? Alright, so I want to focus on getting into chapter 2, and then we'll take our quick little field trip, and then we'll head home, or wherever you want to go.
Where's our field trip?
Huh?
Where's our field trip?
To Balboa Park. No, we're going to... Sorry, it's just going to be around campus real quick. So, I want to first take you back. You remember this? You remember creating this kind of thing?
Yep.
Where would this have come from? What is that?
So,
Be more specific. Vertical asymptote. Where would that have come from? The bottom. So tell me, what would have been the bottom of this possibly? X minus 111. Or some multiple of that, or something. Yeah, good. And then this comes from what? The horizontal asymptote. Comparing the top and bottom's degrees. Remember that? If the bottom power is higher, it goes to 0 because the bottom grows big and the top doesn't do a damn thing. Compared to that, if the top's higher, it goes to infinity. It's not contained then. The bottom can't grow faster than the top, so it just goes to infinity. If they're the same degree, they're lockstep with each other. That's the ratio of the coefficients. So it must have been maybe something related to this. The ratio of the coefficients is 2, so then the horizontal asymptote would have been 2. I'm not saying that that's what that is, but it would look something like that. You guys kind of with me?
Yeah.
Okay. So that's not what I want to focus on. That's what pre-calc was for. Here, I want to focus on retooling how we express what's going on here to get a more efficient way of doing calculus. And depending on what pre-calc teacher you had, they might have shown some of these symbols or not. So at least, hopefully, your pre-calc teacher did something like this. As x goes to infinity, f of x goes to what?
Approaches 2 from the positive side.
I like it. So as x goes to infinity, my function values go to 2. As x goes to negative infinity, f of x goes to 2. Right? You actually could have functions that don't have that same result in both directions. As x, what other point would be interesting, of course? 1. As x goes to 1, f of x goes to... Now here's the question. Now I'm doing this on purpose. Some of you guys might see where this gets a little freaky. Why, the way I've written that, why can you not answer it?
You know which side it's coming from.
Exactly. It depends on how I look at it. In one sense, if I look at it as I approach 1 from above, my values approach positive infinity. If I approach 1 from below, my values approach negative infinity. Now, of course, you could have something where they agree, but you still have to have the ability to look at both directions. You guys semi with me?
Yeah.
Okay, cool. So as x, so I can't even say this really. As x goes to 1 from above, then my outputs go to
Infinity.
positive infinity. As x goes to 1 from below, my outputs go to negative infinity. Cool. All right. There's no general rule here, by the way. This could have been up here and this could have been down there. It would have been flipped to positive and negative, so don't think it's always negative this way. You with me?
Yeah, it's just the direction you...
Yeah, just the direction you see as you're coming in from below.
You're coming in from the negative
It could have
side.
went this way, and it could have went this way.
I
It
know,
would
but
have
it's
been
coming
flipped.
in from the negative side and coming in from the positive.
Yeah, cool. How we doing?
Good.
Semi-decent? All right. So then this, if I say as x goes to 1, I actually can't finish that statement. It doesn't agree. They have to kind of agree to be able to say something there. Does that make sense? So let me ask you something that seems silly. As x goes to, let's see something. As x goes to 1/2, f of x goes to what? I'm trying to make it something here. Yeah, goes to -1. So it doesn't, I mean, this idea of as x goes to something, what's the outputs doing? It doesn't have to occur at these weird-ass places, infinities and asymptotes. It's just everywhere. It's just, these places are kind of silly to talk about because they, of course they agree. It's continuous. Of course they go to the same place from both directions. It's the same damn line. So that's why we normally focus on these weird-ass places. How are we doing so far?
The reason why you can do that right there and not the 1 is because the top half doesn't go to 1/2, right?
Where are we at? Sorry.
You said as x goes to
Oh
1/2.
yeah, so as I go to 1/2 from above or from below, they both agree on -1.
Okay, but
That's why I'm allowed to do this.
But you don't have to specify on that one, but you do on this one
Because
it's
these
two.
don't agree.
Okay.
So I could have, right here, I could have said a
Because it's
plus
just
there.
one. It's one line.
I
Right?
could have said a negative there, but then it would have still been
Yeah, alright.
So then at that point, if they agree, I'm just going to screw the plus or minus. It just goes to -1 when I approach 1/2. I don't care which way
It's
I
like
go.
a regular line.
Oh, exactly. It's continuous, so there's no possibility that they disagree. Does that?
Yeah.
Okay. And of course, later this semester we'll have a formal definition for what continuous means. And I've already used that word a couple times. I don't know if you've heard that word in the context of math graphs before. Continuous, just really the kind of a way to describe it is you don't have to lift your pen up to draw it. That really effectively captures it. A lot of my math teachers that I took, they didn't like that definition, but it actually captures continuity. Even if you have funky places like things called cusps, you have functions that actually look like this. This is really freaky, but it's still continuous. I didn't have to pick my pen up to draw that, so it's still continuous there. Something that wouldn't be continuous would be like this. Obviously, right? It's discontinuous. Oops, it jumped up there somehow. Okay, maybe. Okay. So what I really want to focus on right now, before we get into that kind of stuff, is how do I write this? This is too much. You know, math people, we don't like all this shit. We want something more condensed. We don't want to write all this all the time. So instead of writing all this, we really write this as the limit x to infinity, like that. So some of you guys have seen that before, some of you guys haven't. But it kind of makes sense. It's the limit. It's what it looks like it's going towards. So when you take limits, I can't get to infinity for one thing. So limits never get to where they're going. They just say, where does it look like I'm going? So as I approach, I could have an open circle there. And I wouldn't care. What's it look like I'm approaching as I come in from above? It looks like I'm approaching -1. And as I come in from below, it looks like I'm approaching -1. I don't get there, and I don't care. Limits, it's kind of like, that's a freaky looking thing. And you get really close, but you ain't going to touch the damn thing. It's all glowing and shit. You know, you're like, I don't know. So does that kind of make sense? It's a little weird example, but I'll try to reinforce it later. How would I write this then?
Limit as x goes to -infinity. 2.
Beautiful. And then this guy, what do you think?
Limit as x goes to +1.
Yeah, 1 from above
F equals +infinity.
equals infinity. I love it. And then, so forth. Same idea. So those mean the same thing. Yeah.
When you said like limits never get to where they were going, isn't it like a frog jumping to the end of the wall and then each time it's...
Oh yeah, I love that.
Half and half.
All right, so here's the thing. Have you guys ever heard Zeno's paradox?
Yeah.
That's what you're talking about.
Yeah.
Zeno's paradox says, he had a couple of different types, but the one that everybody knows is Zeno wants to get to the next town. So he's never going to make it, the poor dude. Because in order to get there, he's got to go halfway. And he's got to go halfway from where he still has to go. And then he goes half of that. He's never going to make it there. Now, of course, Zeno's like, I made it there, dude. What the hell's your problem? So when I was a student, I heard that for the first time, and I said to the teacher, why don't you just tell him it's twice as far as it really is? So when he goes halfway from it, he's like, I'm here. Oh, thank God. And the teacher's like, no, that's not the point, but those kind of things, you got to be careful how you present them because they are kind of silly. It's like, of course I got to make it to the damn town. But then you start taking physics and you start really thinking about how far can we really break stuff down? And what does it really mean when you get to the point where you're getting really tiny from normal experience? And that's when you start talking about, the Planck length and things like that, if you ever get into physics. That's where Zeno's paradox all of a sudden has real meaning. But we're not going to do that. So it's sort of like that in a way.
It gets closer and closer, but it never
You
gets.
do this. All right, so what's the limit as x goes to 2 from below of f of x?
It's 2. -2.
Yeah, as x goes to 2, the outputs are going towards -2. Now, right there, is everybody cool with that statement? Then you understand what I mean by the limit never gets there. Because what is f of 2? Nothing, not defined, undefined. There is no f of 2. There's an open circle there that doesn't go anywhere. The limit doesn't care. It just says, what does it look like this is going towards? Right? So the limit as x goes to 2 from above is
-2.
-2. So then what's the limit as x goes to 2, period? Can I say that?
Yeah. Yeah. If it's going
Yes. Remember, if they both agree, if they agree from below and above, I can officially say the limit as x goes to 2, not clarifying it either way, is -2.
It's when you have those gaps, right?
That's when things get freaky. Yeah. But even this is our first little hint of freakiness. It doesn't matter if the function's defined there even. Limits just say, what does it look like it's going to? And I got this song in my head. Going to... I don't know. It's a random thing that happened to me. Thank God I don't know the words, so it's going to go away pretty soon. Oh, cool. All right. So that this notation is going to rule our life basically for the next week and a half or so. Especially for the next few bits here. So I want to come back to something. Let me see. There's a lot of different ways to do this, so I was trying to plot out a good way to do this. You maybe have heard this before, and if I would have thought about it, I would have brought an example. But if I started twirling this thing, right, and somebody cut it or something at some point, where's it going to fly? How's it going to fly? Which direction is it going to go? So as it's rotating around, as I'm twirling this thing, if I cut it right now, it's going to keep going in that direction it was going at that moment, right? It's not going to. The only reason it's going in a circle is because it's being pulled in towards the center. The minute, the millisecond that you cut that off, it's going to start. It's just going to keep going in the direction it's going in at that moment because the acceleration is gone now. It has no reason to go in a circle. So when I have circles, the easiest thing to think about. If I cut that rope right here and it's going in this direction, it's going to keep going like that. Does that make physical sense? You might have seen this. What am I thinking about? Maybe some unfortunate. What's that game where you hit the ball and it goes around the tetherball? Some unfortunate tetherball accident where the string came off and it went flying and hit some kid. Oh no! That's kind of like the thing I have in mind. This is what's called. If I look at this whole line, this is called the tangent line. Now, if you try to define the tangent line as the line that intersects the curve once, you get into some trouble, right? And here's why, real quickly. If I have something, and really what it should be is somehow that tangent line should be parallel at that point. Does that make any sense? I mean, where is this thing flat? Where would this thing be flat, the tangent line? Where would it be a flat tangent line?
At the point on the circle.
Would it be here? At the top and the very bottom, right? So, and sure enough, at the top and the very, if I look at it like this, right here, it's basically going in this direction. So it's going to be parallel. It's going to be moving in the same direction something would be at that point. That's really the definition of tangent line. So if I drew a graph like that, and I said, what's the tangent line here? Well, it should be, if I just move my hand along, it should be going that way. But if you extend it, it hits the damn thing again. So really, when they say it hits once, they mean it hits once in a you're going to love this, in a neighborhood of that point. Very small area of that point, right? Just right there. Doesn't matter what happens way over there. I don't care. You guys semi with me at the moment?
Where the slope is the same, right?
Yeah, it's gonna have the same slope. That line would have the same slope that the curve would at that point.
At that point.
Exactly. And this is how we're actually trying to get. When I talk to my pre-calc students, even my algebra students, I sometimes scare them with stories of what calculus is. And all calculus is And you're here, so this is good. All calculus is taking the idea of slope, which up until this point could only mean lines, because it never changes. Once you see the slope there, well, it's the same everywhere. But what do you need to determine the slope of a line? 2 points. Shit. Here, I want to know the slope at that point. And of course, why does that make sense? The instant you move away from that point, the slope is going to be a little different. A line, I don't care where the hell you go. It's the same everywhere. Who cares? The minute you don't have a line, you have some kind of curve, now I got to be very at a point, at a point, at a point. So our first...
So at every point, there's a different tangent line.
Exactly. Every point has kind of its own tangent line. Of course, some you're going to have repeats. Think about the cosine. You're going to have...
The min-max thing. The same slope if you...
Oh, yeah, exactly. Places where the slope is 0 are going to be your mins and maxes, possibly. I love it. So here's something. Now I'm going to finally shut up for a little bit and let you guys do something. Let me set it up. Let's take a nice, easy function, x squared. And let's say we want to figure out what the slope is at the point 2, 4. Thankfully, that's a point on that graph. That always helps. All right. So I want to know the slope is right there at that point. So if I have parabola of course we got there, we got there, we got there, make it nice and fat. So I want to know the slope is right there. Algebra fails us, but it's not algebra's fault. I mean, it's built on requiring 2 points, and I want to know at 1 point. So the best we could do right now to estimate this is to start maybe at 1, 1. And what's the slope between those points? Now this is what would be called a secant line. Notice how these are all trig words. Interesting. So if I have the line between these 2 points, that's the secant line. That's from the Latin meaning intersecting, and tangents from the Latin for touch. Yeah?
Do they have any connection to the trig functions?
Yes. They do. Will I describe it right now? No. It'll be coming up soon. Can you find, real quick, just take a minute and find the slope between those 2 points? So this will be secant line number 1. And of course the slope is 3. Cool. Now, how do I refine my estimate? That's a bad estimate, of course. My goal is to get the slope right here. Algebra requires, and in fact, let me write this down, because this actually becomes really, really important. It's not going to remain this easy, but what's the formula for slope?
Y squared.
Careful. Yeah. Let me refine this a little bit. Y2 is what I get when I plug x2 in. Is that right? Of course. Right. When I plug 2 in, I get 4. So let me write this a little better. This is f of x2 minus f of x1 over x2 minus x1. Is that cool? I really haven't changed a damn thing. We know that f takes the place of y, so there it is. Okay, cool. So how do I make this a better estimate? Yeah, get the points closer. So I could pick a point a little bit closer. And let me make this a little bit easier on us. If I pick some point x, y, and of course, is everybody kind of with me? It kind of makes sense. I want to step the point in closer and closer to what I really want. So I have a bad estimate right now. Well, let me get a little closer. Let me get a little closer. And the reason we're doing several is so I can see if there's a pattern. If it's telling me what it's... If I see 1.9, 1.99, 1.9... Okay, it's trying to tell me 2. Right? But I need several to see what that pattern would be. If I pick a point x, y, what is the slope going to be? Between 2, 4 and x, y.
It's going to be 4 minus y, 2 minus
I like it. And let me just, for the sake of things different, write it like that, just to make it a little easier to look at. I can do it either order I want to, right? Of course. The sign's not going to change. And what is y specifically in this problem? X squared. So even better. You guys still kind of with me? So effectively what we did here was we did that for x equal to 1. So if you do for x equal to 1, you get x equal to 1, you get 1 minus 4 over 1 minus 2, you get negative 3 over negative 1 is 3. Yay. So how do I step closer then? I let x equal 1.5. Let's make a little table out of this. What's that slope? We'll go 1.5 into that little equation we just made up. I'll do it with you. Got it.
3.5.
Yeah, I get 3.5. Does that make sense? If I step my point a little bit closer to 1.5, doesn't my slope get a little bigger?
Yeah.
As it come around that corner, it's getting bigger and bigger, so that kind of makes sense visually? I guess so far? So, I mean, this is the really cool thing to realize about calculus. I'm not saying it's going to be an easy class. I am saying it's based on a very simple idea. Taking the thing we know and working with it. Now, this is not calculus yet. This is all algebra and trying to use a pattern to get to it. Calculus is when we start saying, screw all this shit. Let's get some shortcuts. All right, that's going to be the calculus. It's when we marry limits with what we're doing. Do you see how the limit idea comes in? And the limit that the point that I use is at that point. And what's really cool about limits, I always need 2 points. But if I take the limit as the point I use approaches this, I never get to that point. I always have 2 points. And that's why the algebra is still cool. It's like, oh good, I still work. Right? I guess that's the thing about limits. Limits never get there. So if I take a limit as that second point, see that second point? I was here, I stepped in closer, I'm going to step in closer. The limit as that approaches this. So do they ever actually are right on top of each other?
No.
Never.
Super close.
The limit never gets there, it just gets super close. Right? I like it. Okay. So what about 1.9? Of course, I'm waiting for somebody. If I was in this class, I'd go, man, let me just do 1.9999999. Screw this shit. I don't blame you, but let's see what happens. What do you get?
3.9.
Yeah, 3.9. And then 1.99, you're going to get like 3.99. So what is it trying to tell me then? Slope is approaching, it looks like the slope is approaching 4. So it looks like the slope should be 4 right there. Can I say that definitively? No. It could actually be 3.9999992. I don't know. But it looks pretty much like it's trying to tell me it's going towards 4, yeah.
So at that point, at that given point at the secant line 2, 4, this, and where you're getting closer and closer, that point's 4.
So it looks like, with my secant work that I've done, it looks like the tangent line would have a slope of 4. All my secant lines seem to be approaching 4 when I get really, really close. So secant lines means you have how many points?
2.
2. It actually means at least 2, but 2 for this. And tangent line means you have 1. So that's what we're always trying to get to.
So my question is, if you picked a different point on that parabola, would it be a different...
Oh, like a different... This is like my main...
Let's say you picked like 3, 6 or something like that.
Well, 3, 9.
Yeah, like, would it be a different...
Oh, hell yeah. Because then as I go
Because it's a
further, what
different-
happens to
it's
my
a-
slope?
It curves.
It gets bigger and bigger. Right? So the slope here looks to be 4. At 3, 9, it's going to be bigger than 4.
Yeah.
Okay? And of course at 0, 0, it's flat. It's 0. And then back here, the slope is going to be
Negative.
negative. Cool. So you can actually see, if I draw on some tangent lines, you can see, coming around the corner, what's happening to the tangent lines that come around the corner and they go up like that. You with me? Okay. So pre-calculus was graphing hell, calculus is definitely going to have some new ways to analyze graphs, but it's not going to be quite as intense as pre-calc was. That's what pre-calc was for, was to make this stuff easier so you don't have to worry about all the other crap you get in pre-calc. Yeah.
When you're saying that, it, like, M approaches 4, how accurate do you have to be, because you only went to 3.9?
That's the, this actually is exactly 4, but that's the shortcoming of doing it this way. There's actually more than just this. But when I see the pattern, like I said, it could be the pattern is leading up to 3.9 to 9992. But I would argue that's basically 4 for a lot of intents and purposes, right? But that's the shortcoming. So that's why we want a more algebraic way, I'd say, in terms, but a calculus way of determining that. A way it's calculated, not observing patterns, but actually calculated. So that's going to be the real way we're going to do it. So we've seen that before, where we do estimates. Like when you first learn how to find solving a system of equations. You first learn to do it graphically. That quickly becomes a crappy way to do it, because what if the answer is 1.79 comma 2.84? Then you're giving the estimates, and then we learn an algebraic way to do it, and then we get the exact answer. That's exactly what's happening here. We got estimates, it looks like it's going to be this, and we want to work towards the definitive way to get the right answer. Yeah?
When you take 1.5, what are you plugging into to get 3.5?
This formula.
And you just got the x squared because f of x equals
X squared, exactly. So it's y,
But you plugged in y.
but y for this curve is always going to be x squared.
Is it always going to work out like that?
Always. You just look back at what your definition is, and that's what's going to go up there.
Okay.
Cool. Okay. We're going to try to keep time. Oh yeah, that's right. Now I do want to say this. So let me show you one little thing that's actually a little ahead of us, but I want to do it just based on the little conversation we just had about how accurate is this. What we're actually doing is we're looking at this, and what x value do we actually want to put in here? We want the value of 2, so we're doing the limit as x approaches 2, and we can see that in our table. We're approaching 2. Cool. And we want to know what that equals. And we're saying it looks like it equals 4. But now watch this. This is where the limits are so kick-ass cool. What can you do with this algebraically?
You can find out.
Factor the top, and what would happen? X plus 2, x minus 2 over x minus 2. Now,
Does that mean there's
let's
a
see if you
hole?
guys know this.
There's a hole.
I like it. You're only allowed to cancel these as long as x is not 2. 0 over 0 sucks. It's actually called indeterminate. Oh yeah, we're going to see some of that later this semester. And it's like undefined to the next power. It's like crazy. So, but what's beautiful about limits? If I can only cancel these when x isn't 2, what's the limit not allowing to happen? X can't be 2. It just gets really close. So I can cancel these. So then I really have the limit as x goes to 2 of this. And of course, when you plug a 2 in, what do you get? You get this, right? You guys kind of with me? Now, don't get me wrong. That is not the way they are all. They are not all going to be that easy. We have a very nice function. We have a very well-defined thing going on. It's not, but that's basically the process we're going to use. But we want to go even further. We're going to want to make general rules for all different types of functions. So we're going to have non-specific kind of functions in here that we have to work with to get a rule created. So this is a very specific function, very nice stuff. That's why this is relatively easy. Does everybody feel decent about?
Yeah.
Yeah.
Just to make sure, so the limit excludes 2 from being an answer, so it opens up a hole.
It excludes 2 from being an input.
Okay.
So any problems that anything would have had at 2, the limit doesn't allow to happen, which is crazy nice. Okay.
So is there a hole there or no?
There would be a hole in the graph, definitely. So the graph of this looks like x plus 2, except at 2, it would have a hole.
Okay.
I love it. So why does the limit doesn't care a shit about that? It's like, I'm not going to get there. Who cares? Yeah.
Can you say the limit is the isotope?
Asymptote?
Asymptote, I'm sorry.
For me, I'm thinking chemistry. I'm thinking how's that? I understand. Limits are related to the idea of asymptote, but in this case, it's not really an asymptote. Yeah.
Where did the equals 4 come from?
Oh, now this is the part that it's made a big deal out of, but I'm kind of trying to make no deal out of this whatsoever. If I let x go to 2, what happens to this? 2 plus 2 is 4. Now, in general, we normally look at limits where I can't do that. Like here, this is the most basic way to handle a problem that a limit has. The immediate limit problem is I can't plug a 2 in, because that would make the bottom 0. So then I just factor and kill the problem. And then I have no problem plugging a 2 in, right? So if they give you a problem, and they will do this, they meaning the book and me, they give you a problem like limit as x goes to 3 of 2x minus 7 over x plus 3. Please, dear God, don't make tables. Don't do all this work. Why is this not hard at all?
You just plug in the 3.
3 doesn't have a problem. I can just plug 3 right in, right? So this function is defined at 3, so I can just go ahead and plug 3 in. So the limit says, what does it look like it's going to? So in this problem, I can't really plug it in yet, because there's a hole there. It doesn't exist there, right? So I can't just plug it in. I had to do a little work, and then I can plug it in. Here, there's no hole there. It's defined there. So if I want to know what it is there, I just plug the damn thing in, and I see what it is there.
So when you plug it in, is that you're finding the slope of that?
No, I want to be careful. Limits are used in the slope analysis. You with me? Because of the fact that I want to bring this point closer and closer, and that is exactly like a limit. So I use limits to find slopes. This is just like a limit problem on its own. It's not finding a slope. It's just finding the limit of this function. As x goes to 3, it's its own thing. So don't think limits mean slopes. Think this. This must be a note because I'm slowing down. Slopes use limits, right? To find a slope, we use limits. Does that make sense? So limit does not mean slope. Cool. So here, what would this be? Yeah, negative 1/6. Cool. Just plug a 3 in. Okay.
And that tells you the slope analysis is going to be negative.
Careful. Again, limits don't by themselves mean anything about slope. All this is saying is when I have a 3, the function is at whatever my scale is, negative 1/6, right?
All right, got you.
My scale is, there's 1. Okay.
The only reason you could do that in that problem is because there's x plus 3.
Because there's if it's x minus 3, then we got to make a table, we got to approach it, right, and see what it's doing. You with me?
Yeah.
Okay. Maybe. All right, how are we doing here? Is that got all that? Okay. Let's see. Blah, 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 blah. All right, here's the neat thing. Okay. So just to get you ready for the homework, and I didn't assign like a crazy amount of this because it does kind of get to you after a while, but your homework is going to involve creating these tables, stepping closer to stuff, kind of getting the idea of the limit, what it really does. But if you do some of that, that's enough. I mean, it becomes busy work after a while, but create a table of values that will help you figure out what this is. And I will tell you something I should have been careful about before. Notice how it just says t goes to 0? Not from above, not from below. So your table, you should actually kind of step towards 0 from above and from below to make sure that they agree. Now before I had a parabola, so I knew that they were going to agree. You kind of with me? So I didn't really worry about stepping in from both sides.
You don't know what you have.
But here, I don't have that graphed, and I really don't feel like graphing it. So I'm going to step in from both sides to see if they agree. So make a little table. let's call this f of t. So just make sure everybody starts off right. What kind of value should you plug in, maybe?
1, negative 1.
Yeah, start off with -1, and maybe -0.1, -0.01. That might be good, or 0.5, whatever the hell you want to do. Do some different things that might be good. Just make sure everybody's getting the same kind of answer. Be really careful about plugging this in your calculator. If you have the old TI, it's going to do this to you. So you don't want to close it until you get the whole, like you're plugging one in, you don't want to close it until you get the whole thing in there. If you have the newer TI, the symbol actually extends, and then you have to push over to get the hell out of it. You guys kind of with me? And you want to make sure that it understands that this is on the top and this is on the bottom. Right?
Couldn't you simplify it before you plugged it in?
I'm trying to keep away from saying anything about that. How would you simplify it? Be careful now.
It'd be t.
Be very
over
careful.
T squared.
Definitely not. Square roots can't distribute across addition, right? So this would not be t plus 3. Right? Is that?
I thought, yeah, it'd be t plus 3 and then -3 and 3.
Definitely not. Right? Square roots of powers can't distribute across addition, so you can't simplify it. Square root of 4 plus 9 would be square root of 13, not 2 plus 3, not 5.
Yeah.
Right? Yeah. Okay. So if you're thinking about that, don't stop. Erase that thought. Never do that. It's bad. Some of this.